Our next speaker is Jitendra Malik. I think all of us know Jitendra. He has done research that has impacted all facets of computer vision. He has taken multiple awards, including multiple Test of Time awards. In fact, I don't think I remember a conference in which Jitendra did not get an award. And he has always led the way in what the community should be doing. In fact, we heard earlier from Larry that the reason we all are using deep nets is because Jeff Hinton was trying to impress Jitendra and, you know, persuade him that CNNs work in computer vision, and Jitendra put him on the test. So we look forward to his talk. I know the reset triangle Jitendra likes is language, action, perception. I don't know if the talk is going to be about this, but we look forward to it. Thank you for being here.
Thank you, Katrina. Okay, so the talk is a mystery because I did not turn in the title of my talk in time, but I hope that mystery will be rewarded. So thank you. So I want to talk about where our field is today and where we should be going. So at one level, we are doing really well in computer vision. And look at the output of sort of one of our leading computer vision systems for object detection and instant segmentation. And this is just amazing stuff. I think 10 years ago, if somebody had said, oh, we will have output like this from computer vision system, I would have said, no way. I mean, I just wouldn't have believed it. And here are some more results. And of course, there are many companies, you know, Google, Facebook, Microsoft, Amazon, and others who are benefiting from the success of this technology. So are we done? What is left scientifically? And I would argue that the easy stuff is done, and there's a lot to be done in the future. And that's why we need to redouble our energy. And I think I totally have enjoyed this, this day, because it's really trying to align the field on what we should be working on next. So let me start with my characterization of what are the problems facing AI today. And I think this will get us all on the same page. And I've picked 4 to highlight. And let me get into them one by one. Limitations of supervision, static data set AI, perception disconnected from action, and the semantic gap. So let's start with supervision. So this is the obvious one that everybody knows about. The success of computer vision in the present era is several things coming together. We had the architecture of neural networks with some innovations that have happened over time, which have helped. We had GPUs, and then we had big data, and we had big annotation. So we had these thousands and millions of images that could be downloaded from the web and annotated, creation of ImageNet, COCO, et cetera, et cetera. And we have had great success with this. But we are now getting into trouble. We're getting into trouble because this paradigm is getting to be hard, because we will never have enough labels for the long tail. So there are some very common categories, and then there are middling categories, and then there are rare categories. But there is long tail of categories for which you just don't have enough examples. Now humans don't have any trouble dealing with that, but computers do. We have this rule of thumb that you want 100 examples for a category, or maybe 1,000 is even better. Then there are labels which are difficult to get from humans. So suppose I want to build a system for doing 3D inference. So start from an image and get the 3D shape. And how do we get humans to output their 3D representation, which is inside the head? It's easy to get them to pick dog as a label, but how do you get them to communicate a 3D shape? Not easy at all. So we're getting into trouble because humans can't annotate what is in their minds. So I think this is getting recognized. The leaders of the field, I mean, Jan has been pushing this for a while, that the secret is we have to get out of standard supervised learning. We need to deal with unsupervised learning, self-supervised learning, and so on. So that's for sure. Second remark, static data set AI. So the progress which we had in the field was through the collection of data sets. And this is like a history of 20 years, and then getting them annotated. And this has been wonderful. And this is why we are where we are today. But is this what vision is about? So these photographs are all taken by photographers. They are disembodied, well-curated moments in time. This is what you get if you put a camera on your head and you move around, and in this case, you're doing grocery shopping. So that's the kind of input that the human observer actually has. And that's the one we work with. And it's multisensory. We have smell, sounds, vision, touch, all of these. There is the important stuff. There is the unimportant stuff. There is the active perceivers choosing what to look at. I mean, if I'm currently interested in cauliflowers, then that's what I will show up in the center of my field of view. And that's what we should be working with if we want to get to human level intelligence at some point in the distant future. Okay, third remark. Third remark is that we have been studying perception disconnected from action, which is completely at odds with what evolution has told us. I think perhaps some Bruno's talk would have hit on this theme earlier, but we know that when the first multicellular animals arose, they could move, but they could see and they could move. And the value of movement, which is to find food in different places, comes in conjunction with the ability to see, because that tells you where to go for the food. And then, of course, that launches an arms race, which results in ever better vision systems, ever better movement systems, camouflage, etc., etc. Well, in the last 5 million years, we have our primate ancestors descending from the trees, starting to walk. The hand is liberated for manipulation, bipedalism, opposable thumb, etc. And that's when we have manipulation. And then if we come to the last 50,000, 100,000 years, this is the era of language, abstract thinking, symbolic behavior. Now, of course, when AI started, it focused on symbolic behavior, logic, things like that. And what has happened over time is that we have gone back to these earlier problems, because in some sense, that's the substrate on which the more abstract symbolic reasoning has been based. So we need to acknowledge that. And the central part here is we can't do perception in isolation, but perception for action, movement, manipulation, etc. Then there is the semantic gap. Now that term has been used and abused many times. So let me say what I mean by this. But let's look at this image. Okay. And today our computer vision systems are pretty good. So they might be able to do something like this. We might be able to detect objects, mark them with pixels, put the stick figure, maybe even connect some objects to the 3D models and so on. But is this really the main point? I think, let me go back to this picture. When I look at this, I don't just see these simple labels of people. What I am telling myself is a story. Okay, so this lady, she is playing music. She's got a bag at her feet, which appears to have some dollar bills. I think this guy is trying to decide whether to put in some money or not, or whether he needs to catch his train, etc., etc. We can spin up all these stories. So that's what we do. And so an interesting question might be, will this man put some money in her bag? Okay, that's the interesting question. This stuff is sort of boring, right? So we are doing the mechanical, boring stuff, and we are not getting the deeper inferences. So certainly something is missing here. And it's not just a problem for computer vision, it's also a problem for natural language. So if we think about AI, the two big branches which have seen a lot of success in the last decade, one is computer vision, the other is natural language processing. So we have amazing capabilities in speech recognition and machine translation and so on. But those systems which can do a great job translating from English to French actually don't know what any of the words mean. It's sort of reminiscent of Searle's Chinese room argument that they can convert from the word bank in English to the corresponding word in French without knowing what banks do. And this is the famous symbol grounding problem, and a lot has been written on that. And the secret for this obviously has to be that symbols have to be grounded in entities in the real world which have sensory motor affordances associated with them. So where should we go next? Okay, and I've now been running this, trying to sell this pitch for a few years, and of course it's now no longer unique, but let me elaborate it anyway, and I will do it from this quote from the famous Turing paper, which most people quote but don't really bother to read. But if they read up to section 6, then this is the quote which shows up. And the basic idea is, and Alison referred to this, that can we try to get intelligence by emulating child development? Now, this was 1950. Now, Turing worked, and at that time, we had a little bit of, we had some work in child development, people like Piaget or Vygotsky and so forth. But Turing, I don't even know how much Turing was aware of that work. But well, in the last 70 years, we have certainly seen major advances in that field, in the field of child development. So when we start as computer scientists, as AI researchers, as machine learning researchers, we can literally, we can benefit from all the work that our colleagues in child development have done. And I'm going to try to push forward a sort of an agenda of research which tries to take the insights from there and tries to convert it to a program of research for computer vision. And it's going to take years, it's going to take maybe decades, but we will not get there if we don't get started. So it's a very convenient way to set this up. I have a paper from Linda Smith, who may be in the audience, so this is a good summarization of what's obviously work done by many, many researchers, which is that we want to talk about embodied intelligent agents. And let's go make it even more concrete. And these are some six lessons from this paper, which I think this should be non-controversial. I think most people would agree that these are important aspects of an embodied developmental approach. So what I want to talk about is how do we take these insights from child development and what do we do to make them operationalized in the world of computer science and AI. So and there is work going on along each of these tracks, and I'll try to build on that. So first is multimodality. So this is kind of obvious. I mean, the child's world, when the baby is playing in her crib, she touches a rattle, so there is touch. There are the motor commands, so there's the efferent's copy, there's the sound, there's taste, there is smell, there's the visual signal. And the beauty of multimodality is that it gets us out of supervision of the boring variety that we are used to in computer vision. And what it replaces that supervision by is cross supervision. So these cues are aligned with each other, and so each cue can supervise the other cue. So, and there's great work which has been going on recently on the connection between vision and hearing, for example. I think vision and touch is very important for robotics. I think the future of robotic dexterous manipulation is with multi-fingered hands equipped with tactile sensing, and that will be a coupling of vision and touch. Okay, so that's point one. Incremental learning, we want to build on previous work. Okay, and so that's again obvious, and but it is not honored in our systems today, right? What do computer vision people do, or machine learning people do in general? We do training end to end on particular tasks. So every task is a separate thing, and this is I think it's very convenient. It makes for the mathematical formalism to be very clean, but I don't think this is where the future is, because otherwise we don't exploit the commonality of tasks. We don't exploit the commonality. So every task has to be learned ab initio. Okay, the next 2 points are be physical and explore. So let me get to the first one. And this is now an infrastructure problem. So what we want to do is to create an infrastructure for embodied AI or egocentric AI. So the kind of vision that I want is the one which, the kind of data that I want is the one which I would acquire if I had a camera on my head or glasses on my eyes capturing images. And I would have that data in a variety of settings. So what we need is to just push the field from one convenient point to a different convenient point. And we are trying to do this. And this is work with Christian Grauman, myself, by some researchers at FAIR and a university consortium, which I'll list shortly. And our grand goal is to collect data in the wild. People going about their daily activities. And then what they have is they have cameras, sometimes microphones as well. And then they will collect video of them performing their daily actions. So the goal is to get to 10,000 hours of video from hundreds of locations. And let me give you a flavor of what kinds of activities we want to capture. We are aiming for activities of daily life. So here's a list from the US Bureau of Labor Statistics of how people spend their time. Okay, so very typical stuff: work, home, entertainment, etc., etc. So we want to get data representing all this. We want to not have cultural biases. So in fact, we have set up a university consortium with 10 different universities. Those are listed here. So not just in the US, but also in UK, in Italy, in India, in Japan. And so the idea is that we will have data in a variety of cultural settings, which is recordings of people's egocentric video as they're going about their daily life. And I hope that this will be the substrate which switches us out from the era of ImageNet and COCO and all these static collection of images to the kind of data that humans get when they are moving around and acting in the real world. Next, we want to have a mechanism for exploration. So how do we do that? So even the data set that I talked about, this Ego4D data set, this data set is still, it is acquired actively by a human because the human is going about his or her daily activities, maybe grocery shopping. But once the data has been recorded and we have the videotape, we have lost an essential aspect. What we have lost is the ability to say what would happen if I looked right, or what would happen if I looked left, right? It's not, at that point, it was active at the moment of collection, but after that it's got frozen in time. So we need to have the ability to do the counterfactuals. So how can we do that? So for that, we need a simulation environment where the real world has been captured and put into a computer. So there is a line of work which people have been doing in sort of between vision, robotics, and ML, which is aimed at creating platforms for embodied AI research. And Gibson was one of the early ones, and Habitat is the simulator out from the Facebook AI research group. And what does it, let me give you a flavor. So what we do is we capture real world environments. Okay, so scans of real places. So this is what these environments look like. So these are not like video games, right? In video games, you author stuff, you make stuff up, right? Because you want to have some fun experience. Here, we are going to take reality and we'll virtualize it, okay? So it might be the same environments in which that observer with a camera on his or her head is walking around. But now we will have this 3D scan. Now, once you have this 3D environment, then the opportunity that it opens up is that you can release agents into this environment. And agents can have varieties of bodies. There could be a human-like body, a dog-like body, whatever. And as the agent moves around, the agent will get appropriate perception, and then it can act. It can choose to go left. It can choose to go right. The experiences it has are going to be dependent on where the agent chooses to go. So what is needed after this is that once you have captured these environments, what we need is to formalize the problems that people should work on in this space of embodied AI. So we can start with the data set. So the data sets here correspond to captures of real world environments in terms of their geometry, physics, etc. Next, we have these simulators. And as I said, there were simulators before, and Habitat is the latest one. And in these simulators, an agent can move around and gets a photorealistic rendering of what's in front of him or her. And then what the agent is trying to do are tasks. So what kinds of tasks could they be? There could be tasks like navigation. For example, I'm in a certain place and then my task is go to the kitchen. Or it could be question answering. It could be a question like, what color is the car? So if I'm asked that question, what I have to do is I have to know cars are in garages. I should navigate to the garage, look up the car, figure out that the car's color is red, then I can answer that question. So navigation, question answering, language grounding, all of that can be done in this setting. So the idea is that just like the previous generation worked on problems like object detection, instance segmentation, pose, and so forth, the next generation of researchers in computer vision will focus on tasks which they can do inside these simulation environments. And what we are making possible, and everything is publicly available, the software is there, you can download it. The previous Ego 4D data set that I described, it's in the process of being collected. I mean, obviously slowed down by COVID-19, but that data set will also be made publicly available for the entire research community. So once we have that, what kinds of experiments can we do? So I'll give you one example of work from my group. This was actually done before Habitat, but it can be done in Habitat kind of environments. So consider the problem of navigation. So it's a very important problem because in when we did the early days, what we did was navigate. I mean, animals in the evolutionary past had to move around, find prey, find food, etc., etc. And there is evidence that there are strategies based on landmarks and there are strategies based on maps. And in fact, both can be used. And the question was, okay, let's try to see what makes sense. So there's a classic robotic solution for this. This is called SLAM. This is essentially build a complete map of the environment, and then you make it into a planning problem. So it creates an arbitrary partition between the first stage where you build a complete geometric map, and then it's a simple planning problem. Now this seems to be not quite what we want to do. I have been at Berkeley for 35 years. I have never gone around and built a detailed map of the university campus of Berkeley. I doubt very much any of you has got that SLAM map of the campuses that you are in. It's simply not what we do. What we do is something more opportunistic. We go to certain places as part of our daily lives, and we build partial maps of the right areas. So what's the right setup for that? Will this even work? Once you have a simulation environment, we can ask questions like that. So here's this paper from a few years ago. And our basic thesis was that you do not need to build complete maps. You need to build a partial map that's good enough, which you will do as you are moving around. And then we can plan in that paths in that space. And this, of course, was an early paper in a certain line of work now on which there are lots of papers on which all go to show that we can do learned approaches to navigation which do not require a complete mapping of the environment. Let me give you a flavor of another research, which was that we want to use landmarks. So when I go about in my daily life, I don't have maps for everything. I have maps, but they are very approximate and crude. What I do is, I will go up to this intersection, and then there'll be a stop sign, and then I'll turn right, and then there will be a Starbucks, and at that point I will go left, and so on and so forth. There are visual landmarks, maybe a tree, maybe a shop, maybe a sign, maybe a piece of rock which has been handed down from generation to generation in the form of myths among South Pacific islanders, right? That's how we do it. And so the path following can be a sequence of landmarks, and how do we train these in the right way with our usual requirement of sort of a differentiable setup, finding the path where all these landmarks provide us guidance from one point to the next. So we can do that. Social. So let me give you an example of that. So social, of course, is a big area. I mean, this could refer to obviously theory of mind and all of that. What I mean by social is just some variation on the theme of imitation learning. Humans have culture. We don't all have to invent the wheel from ab initio, right? We are not what we were 100,000 years ago as hunter-gatherers in Africa. We learn from our sort of parents, we learn from school, we learn by observation, passively, interaction, etc., etc. So to convert it to a computer vision problem, suppose we have access, we have all these videotapes on YouTube of people performing various kinds of physical activity. Can we use that to train a humanoid to do the same thing? So we can convert from that video to a 3D skeleton doing the same thing. So this is work from Anju Kanazawa, sort of applying those techniques. And then that can become a reference signal for training a reinforcement learning system. And that's what you see here. This is, of course, just scratching the surface. This was movement in free space. Actually, we want to learn actions which correspond to interactions with objects and so on and so forth. And finally, of course, there's language. And I've not worked on language much, so I will skip this. And I want to conclude with like some big picture remarks. And the big picture remark is that this is one of my favorite quotations. It's from Kenneth Craik from 1943. I mean, he tragically died soon after because he was in a bicycle accident. But he has this beautiful statement. If the organism carries a small-scale model of external reality and of its own possible actions in this world, it's able to try out various alternatives, conclude which is the best of them, react to future situations, and so on and so forth. So what we have are, based on our experience, we have zillions of models. Those models can be of the behavior of objects, how marbles roll down inclined planes, balloons filled with hydrogen rise, water spills, okay? They can be models of social behavior. They can be models of, and this is like a classic idea, scripts, schemas, frames, whatever you want to call it. When I go to a restaurant, I know what sequence of things will happen, and my behavior in a particular situation is based on my prior experience of that stereotype behavior. So a lot of what we call common sense is merely in a collection of models. These models which have been acquired from our past experience. So I believe that that's the way we will, that's going to be an important step in our journey to ever more advanced artificial intelligence. And we will learn from perceiving and acting in the world, and by acquiring these models, which will be used to interpret the world in front of us. And okay, so this is like the summary slide, which lists again some of these core ideas from child development. And I've tried to tell you about ways in which these can be concretized. And in particular, I've emphasized a lot the development of research infrastructure. So in physics, they have to build these super colliders, superconducting super colliders, or these fancy machines which cost billions of dollars, by which they can accelerate particles and have them collide with other particles, and that's how they do science. So in our field also, we need infrastructure, and the infrastructure is in the form of data sets, simulation, environments, and so on. And that's what we are trying to do, which will enable and facilitate this kind of research. I want to make one more remark, which is that the ideas that are in this previous slide, which are inspired from child development, have triggered people in machine learning, and they have come up with various formalisms, and here's a list of those. And you might argue that, okay, then what do we get from looking at child development that have all the insights already been squeezed out? And I would argue very much that is not the case. I think many of these models that have been proposed are quite simple and quite simplistic, and sometimes that just comes from the desire to have a simple mathematical framework. But they miss out on a lot of essential aspects of the problem. So, for example, continual learning, lifelong learning. What does that mean in machine learning today? A lot of it is basically about, okay, I'm going to get a series of examples from which I'm trying to develop a classifier, and then after a while I don't get to see the old examples again, and I keep training the system, and then there is what's called catastrophic forgetting. So I forget being able to do correctly on the old examples. Now this is fine. I mean, it is an aspect of human memory that we don't, as we are acquiring new concepts, we don't so quickly forget old concepts. But this is such a small part of the notion of lifelong learning, right? In lifelong learning, we have representations which we build on in various ways. And we are not doing that in computer vision or machine learning. In fact, we are often solving each task independently, which is the opposite of what you want. So I could go on, but my goal here is to encourage people to go back to the source, look at the raw experimental findings from our colleagues in psychology, use that to construct operationalizations and models which tackle problems in their full richness. And I cannot do better than to quote Alan Turing, because I call this talk Turing's baby. So I must end with this inspirational quote from Alan. Thank you very much.
Thank you very much, Jitendra. So one question from Pablo Ardalaz is, how do you organize all those multiple models, which is a beautiful phrase that common sense is a collection of models, right? I mean, many people are looking onto static knowledge graphs, right? But how do you organize those models, the perception of the world? How can essentially, or this is just, implementation details?
No, I know it's a good question, but I don't know the answer. I actually don't even know how to acquire all these models. I just know that we need to acquire them. So, because let's take these models like schemas, right? So the AI people from the 70s and 80s, what they would do is they would hand code this. So they would hand code what happens in a restaurant, and look how that turned out, right? What we want to do is to acquire these from data. So we want to acquire these from video clips corresponding to our observations. Okay, but that's easier said than done. I think that machinery is not there. When we do video understanding today, we do very crude, simple-minded stuff. We label people as running, jumping, whatever. Okay, that's at the level of a single second. What we want is long-form video understanding. We want to understand the causal structure of what happened. And we are simply not there yet. Once we have that ability to use that kind of data, then we will, I think, get and robustness, which we don't have in these handcrafted systems from the 70s and 80s. So the short answer is long-winded, but my short answer is, I don't know. But we need to leave some problems for the future, right?
All right, we're here to ask questions. That's right. So can I ask one question? So my question is, when would we feel successful? When is a small test for our systems to show that, yes, we have acquired common sense? Do you expect better tracking and better machine perception or do you expect that home robots will show up? And if indeed the final application is the point, then given how much money has been spent on self-driving cars, why don't we tackle the common sense of driving, and how do we handle, you know, construction sites? And given that the platforms are there, the cars are out there trying to interact with the world, right? And this is where they also have problem. They have problem in the common sense on the, you know, edge cases and so on.
Yeah, so I have two answers. One is that I like home robots more than I like self-driving cars. Okay, I think home robots can be very helpful to people. I think they can be helpful to elderly people. They can, I think that they would need to have versatility. So both from the point of view of the science and in terms of benefit to society, I think I'm more for home robots. For self-driving cars, I think there are two ways you can go about building self-driving cars. One way is that you just collect tons and tons of data and you hope that every weird case shows up in the data, right? And that's what people have been doing. And I think that approach is, in my mind, always going to be in trouble, because there is a very long tail of rare cases. And I started my talk with that basically there is a long tail and there'll be rare cases and even rarer cases and even rarer cases. Now, what do humans do? I think humans can do ab initio reasoning because they have models. So my canonical example would be, okay, when my 16-year-old kid goes to driving school, he's not just learning driving in those 2 or 3 months where he's learning everything about vision and action and so forth. No, at the age of 16, he has acquired a lot of models over time, which come in, and now the driving instructor just teaches basic rules of the road, some element of coordination. So let me give you an example. I'm driving on a freeway. There's a truck in front of me. And from that truck, some junk falls out at the back. That junk could be like sheets of newspaper, in which case, or some billowing plastic sheets, in which case the right thing I should do is just keep driving in front of this. Or it could be like big chunks of metal or rock, in which case I'm in trouble if I try to keep driving straight. What I should do is try to take a risk and switch to a neighboring lane. How do I do this? I have not encountered this case before, but there's a lot of common sense physical reasoning which has gone in behind what I did in that 1 second of inference. Are we going to acquire that in the context of driving? Or are we going to acquire this in the context of life and growing up? I want to argue that we should acquire it in the context of life and growing up.
Yes, that makes total sense. Like when we go to play the video game is what we have learned before while growing that helps us tackle the video game. So you're saying the home robots are more like the toddlers, right?
Yes.